Alright, so section 8.7.1, we're talking about graphs of rational functions. So far we've talked about the graph of the parent rational function, which is f of x equals 1 over x. We know what that looks like, and we know how transformations to the equation transform the graph. So today, we're going to take a look at some other more complicated rational functions. Some rational functions create very different kinds of graphs from those we are familiar with. In this lesson, we will learn how to predict some of the features of the rational function's graph by studying its equation. When examining a rational function, it will often be helpful to look at the equation in factored form. Right, so you see 3 examples of some new rational functions on this slide. And some of them, actually all of them, are more complicated than the ones that we've looked at so far. The first one here, y equals x cubed minus x squared minus 8x plus 12 over 6x squared plus 6x minus 12. We have a cubic function on top and we have a quadratic on bottom. This is much more complicated than we've looked at so far. And look at the graph. It looks like it has 3 very different parts to it, including maybe some asymptotes in there. Much more complicated than we've seen so far. Second equation, y equals 1 over x squared plus 1. Not as bad as the first, but definitely different than what we've done so far. And you can see the graph there. And then the last one over here on the right, y equals x minus 1 divided by x squared plus 4. And you can see its graph there. We've seen the rational functions have regions that are undefined. These undefined regions can be in the form of an asymptote or a hole in the graph. Now the graph and the equation on the left, right here, y equals 1 over x minus 2. This is very familiar to us. This is the parent function, 1 over x, which we talked about. Except the x minus 2, we know shifts it to the right 2 units. And so, our vertical asymptote, instead of being at x equals 0, is now at x equals 2. This is something that we've done previously, right? This should be familiar. The horizontal asymptote, still at y equals 0, because there's been no vertical shift. So we're used to seeing these asymptotes. Well, in the second example over here, y equals x cubed plus 2x squared minus 5x minus 6 over x minus 2. There's no asymptote. There's what we call a hole in the graph. And you can see it right here. This hole is a single point where the graph is undefined. It does not exist at that point. And we're going to take a closer look today at how do we determine, just by looking at the equation, where there might be asymptotes, where there might be holes. So starting with the vertical asymptote. The equation of the vertical asymptote, or asymptotes, can be found by finding the roots of the denominator. A rule for finding a hole in a graph. A hole in a graph occurs at values that make both the denominator and numerator 0, provided there are no vertical asymptotes at these values. So the rules for finding where the horizontal asymptote occurs. First rule, if the degree in the numerator is less than the degree in the denominator, the horizontal asymptote is y equals 0. Second, if the degrees of the numerator and denominator are equal, the horizontal asymptote is y equals a over b, or a divided by b, where a and b are the leading coefficients of the numerator and denominator. The third rule, if the degree in the numerator is greater than the degree in the denominator, there is no horizontal asymptote. Right, on this slide, we have 4 examples Now we're going to sort of focus on the equations, and we're going to apply our new rules. So we have the graphs to verify what we find from the equations. So in part A, y equals 1 over x minus 2. Again, this is a familiar rational function. We know it's that parent function 1 over x shifted to the right 2. But let's apply our rules now. Start with the vertical asymptote rule, which we just learned says the equation of the vertical asymptote can be found by finding the roots of the denominator. So if we take the denominator, x minus 2, to find the root, we set it equal to 0, and we solve for x. Well, we would solve for x here by adding 2 to both sides, and x would equal 2. So this is the equation of the vertical asymptote, and just like we know, there it is right there, x equals 2. Right? So the rule works. Now let's look for the horizontal asymptote. So the rules that we just learned, the first rule applies. If the degree in the numerator is less than the degree in the denominator, then the horizontal asymptote is at y equals 0. Well, the degree in the numerator, well, there's a 1 there, right? There's not even the next term in the numerator. And so it's less than what's in the denominator, so there's our horizontal asymptote at y equals 0. Let's go to part B. So we have y equals x minus 2 over x minus 2. Now, if you came across this equation without seeing the graph, you might think to yourself, okay, I'm going to try to find the vertical asymptote. So I'm going to find the root of the denominator. So I'm going to take the x minus 2, I'm going to set it equal to 0, and I'm going to solve. So we would solve this simple equation, and we would get x equals 2 again, which might lead us to think, oh, well, there should be a vertical asymptote at x equals 2. But we just learned that the rule for the whole is that if this value makes both the numerator and denominator 0, then it's not a vertical asymptote, it's just a whole. And of course, if we plug in 2 to the numerator, it also would equal 0. And so that's why that whole exists right there. Part C, we have y equals 1 over x minus 2 squared. Okay, let's start with the vertical asymptote rule again. Find the root of the denominator. Well, x minus 2 squared is x minus 2 times x minus 2, right? So we set that equal to 0, and we solve for x. Well, our two factors are the same. They're both x minus 2, so we really only have to solve it once in this case. And as we've seen already, x is going to equal 2. And that 2 does not make the numerator 0 also, so we know that there's a vertical asymptote at x equals 2, right there. Now for the horizontal asymptote. Again, if the degree in the numerator is less than the degree in the denominator, then the horizontal asymptote is at y equals 0. And again, we see there's a 1 on top here. The degree in the denominator would end up being at 2. So the degree in the numerator is definitely less. There's our horizontal asymptote at y equals 0. And we finish up with part D. So we have x minus 2 squared over x minus 2. Alright, so again, let's sort of start with the vertical asymptote rule. Find the roots of the denominator. So the denominator is x minus 2. Solve for x. Get x equals 2. You think, oh, vertical asymptote at x equals 2. But then you look a little more closely and you see that if x equals 2, then the numerator would also equal 0. And so there's not a vertical asymptote, there's actually a hole right there. So next we're going to look at an example where we don't already have the graph, and we have a fairly complicated rational function. So y equals x squared plus 2x minus 3 over x squared minus 2x minus 8. Now the first thing that we're going to do is we're going to factor the top and the bottom. So we're going to set up our parentheses. If the second sign is negative, then we automatically have a plus and a minus. X squared factors into x times x. And 3 factors into 3 times 1. And we want that middle term to be positive. So we're going to put the 3 with the positive, and we're going to put the 1 with the negative. Next, we're going to factor the denominator. Again, second side is negative, so we automatically have a plus and a minus. X squared factors into x times x. 8 factors into 8 times 1 or 4 times 2. So we have to decide which pair of factors we want. Since we need a negative 2x as that middle term, even 1 won't get that done for us. So let's use the 4 and the 2 and put the 4 with the negative and the 2 with the positive. Now we're going to try to find, are there any holes in the graph? What are the x-intercepts? Are there vertical asymptotes? If there are, where are they? What are the y-intercepts? And what are the horizontal asymptotes? And we can do all of this just by working with this equation, okay? The holes in the graph. We know the rules for finding the hole is there a value that makes both the denominator and the numerator 0 at the same time, right? Well, if we take a look at our denominator, we have the factors x plus 2 and x minus 4. So the question is, what does x have to equal for the denominator to be 0? Well, if you solve both of these, x could be negative 2, that would make this term 0, or x could be positive 4, and that would make this term 0. So the question is, does negative 2 also make the numerator 0? The answer is no, because you can plug it in and see that none of those terms would become 0. But positive 4 also makes the numerator 0. And again, the answer is no, because you could plug it in and it wouldn't equal 0. And so we can conclude that there are no holes in this graph. Alright, next thing we're going to try to find is the x-intercepts. X-intercepts are like the roots and the zeros, correct? To find the x-intercepts in a rational function like we have, we're going to find the roots of the numerator. Find the roots of the numerator. So we have x plus 3 times x minus 1, and we need to find out when that equals 0. So we take each factor there, x plus 3, and we set it equal to 0. X minus 1, set it equal to 0. Solve for x. Here x would equal negative 3, and here x would equal positive 1. These are our x-intercepts. Next thing we're going to try to find the vertical asymptotes, so we have to know our vertical asymptote rule. To find the vertical asymptotes, we find the roots of the denominator. Well, we actually already did this when we were trying to find the holes, but let's do it again. X plus 2 times x minus 4 equals 0. So we know x is going to equal negative 2, and x is going to equal positive 4. So these are going to be the equations of our vertical asymptotes. Next, we're going to try to find the y-intercepts. We know that for any equation, to find the y-intercept, we plug in 0 for x. So let's do it. So we have 0 plus 3 is 3. We have 0 minus 1, which is negative 1. On the bottom, we have 0 plus 2, which is 2. And we have 0 minus 4, which is negative 4. 3 minus negative 1 is negative 3. 3 times negative 1 is negative 3. 2 times negative 4 is negative 8. That simplifies to positive 3/8, which as a decimal, if you want the decimal form, is 0.375. Finally, we're going to try to find if this rational function has any horizontal asymptotes. So we go to our horizontal asymptote rules, which there are 3 of them. And we also go back now and we have to look at the original rational function here. And if you know your rules, the second rule that says if the degrees of the numerator and denominator are equal, then the equation of the horizontal asymptote is y equals a over b, where a and b are the leading coefficients. Well, there's no doubt that the degrees in the numerator and denominator are equal here, right? So the equation of our horizontal asymptote is going to be y equals a over b, where a is the leading coefficient of the numerator, which in this case it's a 1, and b is the leading coefficient of the denominator. In this case, it's also a 1. So the equation of our horizontal asymptote is y equals 1. So we were able to determine all these characteristics of the graph just by looking at the equation and knowing our new rules for finding asymptotes and holes and applying some old math information about finding x and y intercepts.